Hello everyone. So, today I am going to discuss about a brief on the topic entitled as organometallic chemistry in principles to applications with the aid of transition metal complexes. Firstly, I'll introduce myself to all of you. This is Anubhav Nath. Currently, I am a third year PhD student in the Department of Chemistry at IIT Kanpur. And today I am going to actually discuss a brief set of questions that I have devised, by answering which you will have a common idea or some basic concepts cleared so that you can apply those in your organometallic chemistry to answer some basic questions. The main topic in today's class will be the reactivities of these transitional metal hydrides or their metal carbonyls or their relative activities. And depending on those only, I have devised some 9 to 10 questions. Those I will be discussing in the further slides. So we shall start. The first question is identifying the correct statement among these four options. The first one is the ligands in mutual transposition compete for the metal d electrons. The second option is the trans ligands weaken each other bonds with central metal atom. The third option is trans effect plays a crucial role in oxidative addition or reductive elimination reactions. And the fourth option is none of these. So we will go through all the options one by one, and we'll see what are the correct statements. So the first question is ligands in mutual transposition compete for the metal d electrons. Now you know that the metal has possessed some d electrons. These are not that much tightly bound, and the ligands are there. They can be in cis position or they can be in their trans position. Now, if the ligands are there in mutually trans position, so that the angle between this L1 M L2, that is the ligand metal ligand angle, is 180 degree, then they are said to be in trans position. Now, if the ligands are in trans position, then they are actually competing for the metal d electrons. That is, with which ligand the metal is actually relatively tightly bound. So both the ligands those are in trans position, their pulling power or their effect of pulling the electrons from the metal are actually in the opposite direction. That's why the term competition or compete for metal d electrons is coming into picture. So it is actually true that the ligands which are in mutually trans position are competing for the metal d electrons. The second option is trans ligands weaken each other bonds with central metal atom. Now, in the ligands are in trans position, then both the ligands are simultaneously pulling the electrons from the metal center. Now, if both the ligands are actually trying to pull the electrons apart, then both the opposite bonds are actually becoming weaker, because you have read about this trans effect. In trans effect, the trans position of the ligand metal bond is actually getting weakened, so the bond becomes labile. The leaving group departs itself from the metal center or detaches itself from the metal center, and the incoming group Ig is then bound to the metal. So that is why the trans effect comes into picture. This is the mechanism of operation of this trans effect. Now, when the two trans ligands are trans to each other and both the ligands have similar or equivalent amount of trans effect power, then they will be tending to weaken each other bonds, which is connected by the central metal atom. Suppose L1 and L2 are there, L1 will try to make the M-L2 bond weaker. Also, the L2 ligand will also try to weaken the L1 M bond weaker. Thus, both the ligands that are trans to each other will try to weaken or de-strengthen the bond between the central metal atom. So these two options are absolutely correct. Now the third option is whether trans effect plays a crucial role in oxidative addition or reductive elimination reaction or not. You see, first we have already discussed a lot about this oxidative addition or reductive elimination kind of reactions. In such cases, the oxidative addition is what? What are the requirements of this oxidative addition OA or reductive elimination RE reactions? In case of oxidative addition, the groups that is present may be polar or non-polar in nature. if the bond that is getting oxidatively attached to the metal center is polar in nature, then the two groups that will be bounded to the metal atom will be trans to each other. For example, methyl chloride, CH3Cl. In that case, the methyl and the chloro group will be trans to each other because in that methyl and chloro have different group electronegativities. Methyl has a group electronegativity in the range 2.5 to 2.8, and chloride has a electronegativity in Pauling scale at 3.0. But if the case is similar, suppose the case is methyl iodide, so methyl and iodine both groups have similar electronegativity in case of Pauling scale. But so in that case, the CH3 and the I group will be cis to one another. Same will happen in case of dihydrogen, that is completely nonpolar. So completely nonpolar or less polar moieties will get oxidatively added to the metal center in cis fashion, but the polar moieties, the group that are polar moieties, this will be oxidatively added to the metal center in a trans manner. So in that case, nothing, no trans effect can play any role in determining the rate of oxidative addition, because the only thing that matters in oxidative addition is the oxidation state of the metal. So metals in low oxidation state, that is highly electronically rich metals, will be very prone for oxidative addition reactions. The reverse are actually true for reductive elimination. In case of reductive elimination, two groups or atoms that are cis to one another and bound to the metal center are actually gets reactively eliminated. So in that case, the metal atom should be in its high oxidation state. So in that case, the electronical efficiency of the metal center should be low, or other terms you can say electronical deficiency would be high. So in that case, the atom's oxidation state will drop down from a high oxidation state to a lower oxidation state. So in that case, from +4 it can drop down to +2 for reactive elimination. In case of oxidative addition, the same metal, if it is in +2 oxidation state, it will go to +4 oxidation state. So by that, in case of oxidative addition, reactive elimination, +2 or -2, both these switches are available. For oxidative addition, the increment will be +2. In the reactive elimination, the decrement will be 2. So in none of the cases, in case of whether it is oxidative addition or reactive elimination, trans effect does not play any crucial role, because these are the reactions, thermodynamical reactions. But in trans effect, it is actually the kinetics. It is regarding the kinetic lability of the groups or the bond that is connected to the metal atom. So the option 1 and 2 are actually correct in this regard. Option in case of Q2, the carbonyl substitution reaction, a 17 electron complex proceeds via which of these following reaction pathways? First one is the ligand rearrangement, the second one is the isomerization, the third option is the dissociative mechanism, and the fourth option is the associative mechanism. So the carbonyl substitution reactions in the 17 electron complex, we have to determine what are the possibilities or what is the actual pathway by which a 17 electron complex reaction, carbonyl substitution reaction will proceed. So first of all, if a metal atom is possessing some carbonyl groups or CO groups, then these groups can be substituted. So this depends upon the relative geometry or the stability or the electron count of the following of the concerned complex. So if you can think about this 17 electron complex, this vanadium hexacarbonyl, that is VCO whole 6, is a 17 electron complex. Now the 17 electron complex, because vanadium is a 4s2 3d3 system, so it is a 5 electron species, and since the all the carbonyl ligands are electronically neutral, so the metal atom or any metal carbonyl, the metal atom is staying in the zero oxidation state. So 12 plus 5 is 17. So carbonyl substitution reaction for a 17 electron compound, that is the VCO whole 6. So VCO whole 6 is actually coordinatively saturated. So in this case, whether the substitution reaction is be proceeding, you can think of two possible pathways. First one is the two terms you should actually have a grip on that. First one is the electronical saturation, and last second option is the coordinative saturation. So if all the six positions you see, transitional metals at most can have these six actually tonal species, because the octahedral geometry is the most common one. So in that case, VCO whole 6 is there. So if all the six group positions are occupied, four in the equatorial plane and two in the axial position, So then the six positions are occupied, then the all the positions occupied, so it is called, or it is said to be, a coordinatively saturated system. But if the electron count is less than 18, then it will be termed as electronically unsaturated. So 18 electron complex having all the six positions blocked will be called both electronically and coordinatively saturated. So what is ligand rearrangement? So ligand rearrangement is nothing but when a ligand, a specific ligand is concerned. If suppose you can see, you can think about this benzyl cation, or you can see some long chain aliphatic with say double bond or triple bond kind of thing, carbocation, then the carbocation will start rearranging, and it will start rearranging such a manner so that the nature of the carbocation becomes the most stable one. Suppose it is in the primary mode, then it will be tending towards going to the secondary carbocation mode, which is more stable, or it can go through the tertiary cation also, that is more stable. So ligand rearrangement is one of the prime things in this case. But you can always think that all the ligands cannot undergo this rearrangement. For that, suitable electronical properties and position is required. Second one is most common, that is the isomerization. You have all known about this isomerization. A same isomerization can be of different types, that cis or trans, E or Z, or you can say the stereo electronic configuration, R or S, every other thing. So these are the isomerization. But the dissociative and associative mechanism, that is options 3 and 4, are most important here to actually discuss. In case of dissociative mechanism, what happens if suppose a metal complex is there, it is termed as MLN. So if in case of dissociative mechanism, one of the ligands will be eliminated first. So one of the ligands will first be dissociated. So from MLN, it will be MLN minus 1. Then if you see, if it is going from MLN to MLN minus 1, then both electronical saturation and coordinated saturation drops. Because if it is 6 coordinated, it will go to 5 coordinated. If it is an 18 electron system, it will go to a 16 electron system. So in that case, for case of dissociative mechanism, both electronical saturation and the coordinate saturation falls. So in that case, when the one of the ligand positions will be vacant, then in that position the incoming group will come and bind. So then it will be again electronically and coordinatively saturated. So this is the most probable or possible mechanism for dissociation, or dissociative mechanism we can call it. The associative mechanism is completely different, or you can say completely opposite to that of dissociative mechanism. In case of associative mechanism, the metal atom will invite another incoming group to the moiety actually. So in that it will be, if it is in MLN condition, then the in case of associative mechanism, the other X group will come and bind, and they will form an unstable transition state or intermediate, you can say. So we will term it as MLNX dagger. So in phone MLNX dagger is termed because it is a transition state, it is not that much stable. So in that case, the X, then the one of the L's will be eliminated and the X atom will remain bound. So in that case, the transition state position, they are actually generating this 19 electron or 20 electron, the electronically oversaturated or coordinatively oversaturated system. Now, if the metal atom is quite large in size, when it can accommodate more than 6 coordinate number species or some more electrons around it, then only this associative mechanism takes place. So now the question is regarding this 17 electron complex, that is VCO whole 6, vanadium hexacarbonyl. Now VCO whole 6 is actually having its electronical saturation, not a electronical saturation because it is a 17 electron system, but it is coordinatively saturated. So in that case, it actually proceeds by the associative mechanism, because in that case you see, when the one, it is one electron down from the electronical saturation, that is 18 electron. So it will invite one of the incoming ligand, that is X. So from VCO6 it will go to VCO6X dagger, that is electronically saturated, also oversaturated, because from 17 electron it will go to 19 electron. Also it is actually in a coordinatively oversaturated phase. Now from this phase, one of the L will be eliminated, and then it will be forming VCO whole 5 X, when X is the incoming group. So that is why the associative mechanism takes place. In that case, dissociative mechanism will not take place, because since it is electronically unsaturated, so it can accommodate one of the other groups to come and bind to that and to form a transient 19 electron species. If it had been an 18 electron system, then associative mechanism will not be that much operative, because you see in the downside. Just allow me to use the pointer here. So here see, I have actually stated that this VCO whole 6, this is here 17 electron system that reacts 10 to the power 10 times faster for carbonyl substitution reaction than this CrCO whole 6. This CrCO whole 6, we shall count the electron of this species, this chromium hexacarbonyl. Chromium is 4s to 3d4 6 electron system, and 6 COs each will be delivering 2 electrons. So 6 plus 6 into 2, that is 6 plus 12, that is 18. So it is an 18 electron system. So, in comparison to an 18 electron system, the 17 electron system reacts 10 to the power 10 times faster for carbonyl substitution reaction. So in that case, the associative mechanism actually plays the crucial role in maintaining such a high speed and overcoming the corresponding 18 electron complex, that is CrCO whole 6. Now we shall move to the next slide. So next slide is also two questions are there. First one is the carbonyl substitution reactions of CrCO whole 6 and NiCO whole 4. What is the, or what are the correct options actually? First one is the CrCO whole 6 reacts faster than nickel CO whole 4. This nickel CO whole 4 reacts faster than CrCO whole 6, or the bond energy that is D of CrCO is higher than that of DNiCO, or the bond energy DNiCO is higher than that of DCrCO. So we have this, have to actually go through all the options one by one. In the carbonyl substitution reactions of CrCO whole C, there is always an 18 electron system. So you see here 6 into 2 is 12, and chromium is 6 electron system. So 12 plus 6 is 18. And this, in case of nickel C whole 4, nickel is a 4s2 3d8 system. So it's a 10 electron system, and all the COs will be delivering total to 4 into 2 8 electrons. So 10 plus 8 is 18. So both the complexes are actually electronically saturated. But in this case, you see the nickel CO whole 4 is tetrahedral, but CrCO whole is octahedral in nature. So the CrCO whole 6 complex is coordinatively saturated also. But this nickel CO whole 4 is not coordinatively saturated. It is coordinatively unsaturated, because two empty spaces are also there to accommodate some incoming ligands. So in that case, it will be quite evident that nickel CO whole 4, on account of having this empty vacant space, or you can say this coordinative unsaturation, it can actually invite other incoming groups to perform this carbonyl substitution reaction. So in that case, the associative mechanism comes into picture, and you have seen in the last slide that an associative mechanism, when takes place, the rate actually goes too much high. So VCO whole 6 reacts 20 to the power 10 times faster than NiCO whole 4. So NiCO whole 4 reacts faster than CrCO whole 6. So among option, between option 1 and 2, the option 2 is correct. So now we'll have a comparison between these 3 and 4. The bond energy of DCrCO is higher than that of DNiCO. You see, we have come to a conclusion that this NiCO whole 4 reacts faster than CrCO whole 6. So in that case, you can also predict that the nickel CO bond is actually not that much high, or the bond strength is not that much high. So that's the bond energy of this chromium CO bond will eventually be lower, because it not will be lower, because if the bond energy is higher, then the bond will be broken in much later phase, or high energy is required. So nickel CO whole 4 will react faster because the bond energy is lower, so it takes less amount of energy to break the nickel CO bond, and then it will be reacting faster towards any carbonyl substitution reactions. Similar is not that in the case of the chromium CO, because in case of chromium CO, since the bond energy is also higher, so it will take some less amount, the high amount of time, because it will take much more energy to break the chromium CO bond, and allow it to react under this carbonyl substitution reaction. So you see between option 1 and 2 state, option 3 and 4 state, they're actually correlated or mutually connected, because if the bond energy is low, then the species will be reactive, it will react faster. If the bond energy is high, then the species will be sluggish in performing the reaction. So in this case, options 2 and 3 are the most appropriate ones, that the nickel tetrahedral nickel, the tetracarbonyl nickel reacts faster than hexacarbonyl chromium, and the bond energy of the chromium CO bond is higher than that of the nickel CO bond. So let's come to the fourth question. The fourth question is regarding again the carbonyl substitution reactions at 18 electron complex proceeds via which of the following mechanism. So in the previous slide, I have already told that these 18 electron complexes are those one which can actually reluctant to accommodate some more amount of incoming groups or any amount, because they are electronically saturated and also coordinatively saturated. So in that case, they will first allow themselves to dissociate, and then when the vacant space or the deficiency in electron count will happen, then only the carbon substitution reaction will be taking place. So if the species is a 18 electron complex, then it is actually will be reluctant if it is not having any kind of electronical coordinative unsaturation, then it will allow to have some vacant, create some vacant space in the environment, and then it can allow the incoming group to fall under. Because I can actually compare between this nickel CO whole 4 and this CrCO whole 6 moieties. You see, since CrCO whole 6 and nickel CO whole 4 both are electronically saturated, but nickel CO whole 4 is electronically unsaturated on account of having this tetrahedral geometry. But the chromium CO whole 6 is both electronically and coordinatively saturated. So in that case, the associative mechanism will not be applicable at all, because in that case the dissociative mechanism first has to take place to create a vacant space in the ligand environment, if I am supposing that the complex is octahedral in nature. So since most of the complexes are more octahedral in nature, so generally speaking, the dissociative mechanism will be acting fast, because in that case dissociation will take place. So one of the carbonyl or the CO groups will be eliminated, that will create a vacant space in the environment and also some electronical unsaturation, and then the incoming group will come and be bound to that metal center, and then the reaction will proceed via this dissociative mechanism. So here the correct option is option 3, where because the 18 electron complex carbonyl substitution reaction will take place under dissociative mechanism preferably, but it is not said that associative mechanism cannot take place. The reaction, the question is regarding a general term, whether which of the following pathways will be more applicable or more convenient for an 80 electron complex to proceed in a carbonyl substitution reaction. Now we'll come to the next question, that is arranging the complexes Y3MO CO whole 3. It is a molybdenum neutral complex, because you see these Y groups are all neutral in nature. All the phosphines, acetonitrile, pyridine, and this ethylene diamine, all the groups has this formal charge 0. So the all and COs are actually also neutral ligand. So all the complexes in our molybdenum is actually staying in a zero oxidation state, that is electronically rich, and the ligands are actually varied here. The ligands are Y ligands are PCl3, PF3, acetonitrile, pyridine, ethylene diamine, POME whole 3, and PPH3. So here among these PCl3, PF3, POME whole 3, and PPH3, all these are phosphines. These phosphorus trichloride, phosphorus trifluoride, this trimethoxyphosphine, and this triphenylphosphine. These three groups are actually end-donor ligands, and all these groups are actually p-donor ligands. These end-donor ligands are pyridine, and this is ethylene diamine is bidentate chelated ligand, and this and the other one is the acetonitrile, where nitrogen is staying in its sp electron. So nitrogen is staying in its actually the high electronegativity, even greater than that of 3.0. So this CH3CN nitrogen is sp hybridized and also linear in nature. So now the question is regarding arranging the complexes or in ascending order of their carbonyl staging frequencies. Now we have to actually get to the point that these all the Y groups have some pi acidic character or this pi or sigma donor ability, and depending upon which the questions may be answered. So we shall go through this para. This is written as the more pi acidic character of the ligand Y, the less will be the electron density on the central metal atom, that is molybdenum, and hence less will be the back donation to the carbonyls, resulting in a higher CO stretching frequency. The more sigma donor ligands will increase the electron density on the metal atom, leading to increase in back donation, resulting in a lowered C double bond O stretching frequency. Now let's come to all the entries. You see, all the ligands are actually having this kind of pi acidic character or sigma donation ability. Now, if the pi acidic character of the ligand is high, that is, the ligand is actually able to withdraw the extra electron from the metal center, then this Y group will drag the extra electron density from the metal center. Now, the metal will then be reluctant to push the electron to the carbonyl moiety. So, if the carbonyl moiety is not experiencing any kind of electronical flow from the metal center, then the CO stretching frequency will not be dropped, because you all know that is, if the metal is actually throwing the electron density, then by molecular orbital diagram, if we have a glance, that is the pi star lumo of the CO, that is the carbonyl, then the if the the metal is actually throwing the electron on the pi star lumo, then the population density on the lumo, that is the lowest unoccupied molecular orbital, will be high. Then the bond order of the CO will be dropped, and thus the carbonyl stretching frequency will also drop, because stretching frequency is directly regarded as a parameter of the bond strength. Similar is will thus exactly opposite case will be happening when the ligand will be more sigma donor type and not a good pi acceptor type. So in that case, the Y ligand will throw the extra electron density to the metal center, and the metal will then channel the electrons to the carbonyl moieties. So the more back donation will be happening, and this will allow the CO stretching frequency to be more weaker, and also the CO stretching frequency will get dropped. So we just have to need to understand which of the following ligands are actually here are actually pi acidic ligand, or which one is the more sigma donor type of ligands. So here is the table. So PF3, PCl3, POMEol3, PPH3, acetonitrile, ethylene diamine, and pyridine. Stretching frequencies are tabulated in this table. In case of PF3, the stretching frequency is 2055 and 2090. Two strengths of stretching frequency are there, because one can be cis to the heteroatomic group and other one can be trans. PCl3, the CO frequency is 1991 and 2040. In case of POME whole 3, it is 1888 and is 1977. So PPH3, it is 1835 and 1934. In case of acetonitrile, it is 1783 and 1915. In case of ethylene diamine, the values are 1758 and 1898. And in case of pyridine, the values are lowest, 1746 and 1888. So this PF3 will be in case of these phosphines. So the first four groups are actually phosphines here. First one is the trifluorophosphine. The second one is the trichlorophosphine, trimethoxyphosphine, and the triphenylphosphine. So in case of PF3, since the fluorine atom is the most electronegative one in the periodic table, so it will be dragging the extra electron density. So it is most pi acidic character ligand, so it will drag the electron density from the metal center, and the metal atom will not be allowed to throw the extra electron density on the carbonyls, and then the carbonyl stretching frequency will remain high, because the amount or the extent of back donation will be least in case of PF3. Since the chloride atoms has a less amount of electronegativity than that of fluorine, so in that case the CO stretching frequency will be dropped from PF3. It's 1991, it is reflected from the table. In case of POME whole 3, you can have the argument that is in the oxygen atom is actually even more electronegative than chlorine, so it should lie between this PF3 and PCl3, but that is not the case here. In case of POME 3, not only the pi acidic character of the methoxy group comes into picture, but also in that case the plasar effect, that is the mesomeric effect, the electron releasing or electron donating mesomeric effect also comes into picture, because the oxygen atom has a strong plasar effect, because it is a short atom and it is a very strong plasar effect. So in that case, the back the also the electron withdrawing minus I effect and also electron donating plus I effect, both are actually cancelling each other. That's why the value is actually residing lower than that of the PCl3. The phenyl atoms are actually consisting of these 6 sp2 carbon atoms. That's why the electronegativity or the pi acidic character of the phenyl groups is not that much high. So that's why it is falls under this POMe 3. You can also have the argument the fluorine atom is also very much short in size, so why cannot it show a plasar effect? You see, because in all the cases except halogen atoms only, the plasar effect or the resonance effect dominates over the inductive effect. But in case of halogen atoms, especially in case of fluorine, the inductive effect, the minus I effect, plays a more crucial role than the mesomeric plasar effect. So that's how the all the phosphines are formulated in the table: PF3 greater than PCl3 greater than POMeol3 greater than PPH3. Now the entries 5, 6, and 7 are actually end-donor ligands. Till now we were talking about these phosphorus or the p-donor ligands. In case of this acetonitrile, ethylene diamine, and pyridine, the pyridine is actually showing the lowest carbonization frequency, because in case of pyridine, the nitrogen lone pair is not actually involved in the resonance with the ring, aromatic ring. That's why the lone pair is actually pointed. The lone pair is actually pointed towards the metal atom, and then it will be bound to the metal directly, and it will throw the electron density on the nitrogen atom to the metal center. Now, since nitrogen atom is throwing the electron density to the metal, in case the minus I effect does not come into picture, because the plasar effect from an sp2 nitrogen atom is actually very much high in this case. That's why in case of pyridine, the value is the lowest one, because it actually pushes all the electron or the extra electron density on the metal atom. Then the metal atom challenges the electron to the carbonyl centers. In case of ethylene diamine, since this is actually has a more amount of flexible nature, because you see the structure of the ethylene diamine is NH2, CH2, CH2, NH2. So in that case, NH2, CH2, CH2 is both the nitrogen atoms actually bound to the metal center, which is a 4 electron donor. So in that case, the electron density on the metal atom increases. But since it is a sigma bonded ligand, which is only having the sigma bond, so the flexibility or the rotational ability of the ethylene diamine is higher than that of pyridine. Pyridine is actually consisting of this sigma and pi bonds. So in case of ethylene diamine, the CO switching frequency will not drop as much as this pyridine. But you can say that is ethylene diamine and the pyridine atoms values are comparable, because there is only a 10 centimeter inverse difference between these two, among 1758 to 1746 and from 1898 to 1888. In case of acetonitrile, the nitrogen atom is sp hybridized, so it is actually more electronegative in nature. So in that case, since it is more electronegative in nature, that's why the pi acidic ability of acetonitrile is higher than this ethylene diamine and pyridine. And hence in that case, since the sigma donor ability is not that much high, because the nitrogen atom is more electronegative in nature, in this case it is sp, it is sp3 normally and is sp2 normally. So in this case also, the acetonitrile, the pi acidic character comes into picture, and that's why among all these nitrogen donor ligands, this acetonitrile has the highest CO stretching frequency. So by this actually having this comparative structural evidences among all these phosphino groups and these nitrogen donor ligands, whether this is chelating one or non-chelating one, is a planar one or neutral one, that is a linear one, we can actually have this table which shows which is the ascending order of this carbonyl stretching frequency. So the order goes as follows: this pyridine is less than ethylene diamine, less than acetonitrile, less than triphenyl phosphine, less than trimethoxyphosphine, less than trichlorophosphine, and the highest one is less than the trifluorophosphine, which is having this highest amount of pi acidic character because of the presence of these highly electronegative fluorine atoms. Now we shall come to these basic sets of reactions which will tell us how to predict the product of any reaction. Now the first reaction is between this iron pentacarbonyl and the sodium trimethoxy BH, which is a very common reducing reagent. Now this is actually anionic kind of, this is salt kind of thing, because it's Na plus and this trimethoxy BH is minus. You see all the methoxy groups are electron withdrawing, and also I have said in the last slide that the methoxy group has a strong pulsar effect. So all the methoxy group will push the electron density on the boron center, since the boron atom has a principal quantum number same as that of this methoxy. So the extra electron density will be very high on this boron atom. That's why the hydricity of this hydride is actually quite high. So what will happen in this case? This hydride will attack on this metal center, not in the metal center but in the metal complex. Now since this BOMe whole 3 is a trigonal planar molecule and it's neutral, so it will be eliminated as BOMe whole 3, and this hydride will attack on any of these carbonyl group that is attached to the metal center. Since the carbonyl groups are actually attached to the metal center, so they are also electrophilicity increases. So this hydride will attack on one of the carbonyl and they will form this formal kind of group. So the net anionic charge of this ligand will be, of this moiety, will be counterized by the sodium plus cation. So the product will be Na plus and this CO4 Fe, this formyl, that it will be minus. So what will happen? Nothing but this hydride will attack on one of the C triple bond O bond. The bond will be collapsed on the oxygen, and instead of CO, it will be bound to the metal center as formyl, and rest of the CO4 will be same as such. Coming to the next example, it is regarding the showing an example of disproportionation reaction in transition metal carbonyl complex. So the question is regarding whether a transition metal carbonyl complex is able to show a disproportionation reaction or not. So the disproportionation reaction is the reaction where a suppose an atom is in some X oxidation state. So in disproportionation reaction, it will be going to some X plus M oxidation state, and the other part will be going to the X minus M oxidation state. So the total increment and the decrement will be cancelling each other. So the metal atom or the any atom that is concerned for in case of this disproportionation reaction or this dismutation reaction, the oxidation state increments, so it will be oxidized and reduced simultaneously in a same reaction. So here we shall start with this manganese zero complex carbonyl complex, that is Mn2CO10. It will be reacting with a 12 moles of pyridine at a very high 120 degrees Celsius temperature. So 10 molecules of COs, all the COs will be eliminated. So the products that will be formed are MnPy62 plus and MnCO5 minus. So you see here the manganese atom is in its 2 plus oxidation state, and here the manganese is in minus 1 oxidation state. So I have already told that in case of disproportionation reaction, the increment in oxidation state and the decrement in oxidation state will be the same. So you can argue here that is from 0 oxidation state he is going to plus 2 and minus 1, but it should be plus 2 and minus 2. But the race is not the same, because you have to also calculate the moles of the reaction also. This is the balanced equation where you can see two MnPy62 plus molecules are present and 4 MnCO5 minus molecules are present. So here we have this Mn2CO10. So 3 moles of Mn2CO10 are there. So total 6 moles of Mn are there. So among 6 moles of Mn0, they are producing 2 moles of Mn2. Total increment is 2 into plus 2, that is plus 4. And the total decrement is 4 into minus 1, that is minus 4. So total increment is plus 4 and the decrement is minus 4. That's how in this disproportional reaction, the amount of oxidation and the amount of reaction will be the same. Otherwise, the reactions would not be balanced at all. So in that case, you see from 0 oxidation state, because all the COs are neutral, so it is a neutral complex which is having a Mn0. They are going to Mn2 plus and Mn minus. So this is a classical example of this disproportionation reaction, where a transition metal carbonyl complexes reduces itself to MnCO5 minus and also oxidizes itself with the aid of this neutral donor bind pyridine ligand, and since the moles of these two species are different, they are from 3 moles, they are actually distributing among themselves between 1 mole and 2 mole in the 1 is to 2 ratio. The reaction temperature is quite high, that is 120 degrees Celsius. Otherwise, the disproportionate reaction would not take place at all. Now, in the next slide, we'll be again discussing two basic examples regarding what happens when VCO whole 6 minus is reacted with a Bronsted acid. So, VCO whole 6 minus is a very popular metal carbonylate. So from metal carbonyl, if we reduced it by one electron, it will be a metal carbonylate where the metal atom is having a negative charge. Since the metal atom does not want to stay in its low oxidation state or this high electronical enrichment, so these are very unstable and reactive in nature. So whenever a VCO whole sigma such kind of metal carbonyl is treated with a proton source, that is a bonded acid, then it will be actually getting oxidize, and H plus, that is bronze will get reduced to molecular dihydrogen. So here it is written that is protic compounds may affect oxidation of metal carbonylates with the regeneration of neutral metal carbonyls with concomitant release of molecular dihydrogen. So in this case, what happens? This is a reaction between an anion and a cation. In that case, this VCO whole 6 minus was there, which is a 19 is a 18 electron complex because vanadium is 4s2 3d3 and one more electron is there. It's a 17 electron complex plus one is 18. So from 18 electron it is coming to a 17 electron species, and this proton H plus source will be reduced to molecular dihydrogen. It was in its plus one oxidation state, but now it is in its zero oxidation state. So in that case, this metal carbonylate is acting as the reducing agent and H plus is acting as an oxidizing agent. But in case not a bronze acid, but any mild proton source will also do, because you see the methanol or ethanol or alcoholic kind of solvents will also release molecular dihydrogen from this metal carbonylate, that is VCO whole 6 minus. The next question is regarding comparing the nature of the following different metal hydrides, which are HCO whole 4, H2FeCO whole 4, HFeCO whole 4 minus, and HMnCO whole 5. So here is the example where we will discuss about the properties of metal carbonyl hydrides. The complex, this HCOCO whole 4 has a very low melting point. Actually, all these kind of hydrido metal carbonylates are actually having very low melting point. This HCOCO whole 4 is having a melting point minus 26 degrees Celsius, and this decomposition point is also very low because lower than the temperature it will be decomposed to the corresponding carbonylates. It is minus 26. If the we record the IR stretching frequency of these molecules, then it is mh, that is 1934 centimeter inverse. Delta 1h NMR, that is ppm. If we হি, হুম? আমি চেঞ্জ করিনি। হ্যাঁ ওটাই ওটা। ওটা পড়তে সুবিধা হচ্ছে। So this delta ppm, that is 1h NMR, is having a minus 10. At minus 10 the 1h NMR is actually coming. Now the pK of this HCOCO whole 4 is having 1. So if we have this kind of pK, it is actually having this comparable acidity with sulfuric acid H2SO4. See, this kind of high metal carbonyl hydride is having such a high acidity. So in that case, if it is having a high acidity, then it is actually residing in the space H plus and CO whole 4 minus. So though we are terming it as metal carbonyl hydride, but it is actually acting as a proton, a very highly acidic proton, because the pK is here is actually 1. So 1 pK molecule is a sulfuric acid, which is a very strong inorganic acid. So now if we come to the next example, that is H2FeCO whole 4. This H2CO FeCO whole 4 is having a melting point around minus 70. It is even more unstable, and it is having a very low melting point. Its decomposition point is also in the range minus 10 degrees Celsius. The 1 inch NMR, the proton actually comes in the region minus 11 ppm. The pK of the corresponding acid is 4.7, which is comparable with an organic acid, that is CH3COOH, that is acetic acid. So also in this case also, the protic behavior of this H that is quite high, although it is termed as a metal carbonyl hydride. In case of HFeCO whole 4, it is the conjugate base of this H2CO FeCO whole 4. The pK is not that low, because it is already negatively charged and it is actually quite stable. So this pK is lying in the range 14. The comparable acidity is with that of water. But in the next case, that is HMnCO5, the melting point is in the region minus 25. The decomposition point is not that much. It is actually relatively stable at room temperature. The highest stitching frequency of the metal hydride comes in the region 1800 centimeter inverse. The P delta of the 1H NMR comes in the region at minus 7.5 in the range, or to minus 8.5. But the pK is actually even lower now. It is 7, which is comparable with sulfur dihydrogen, that is H2S, hydrogen sulfide. So we actually have coined here some basic properties of this metal carbonyl hydride. So depending on those, you can actually have a glance that though they are called hydride, but they have their significant kind of this is protic behavior. So they can act as actually proton, because you see, if they are actually having this pK in the range 1, then how much acidity they can actually perform, how much acidic they are, even in the region of this very strong inorganic acid considered as sulfuric acid, and is also in range of this acetic acid, this H2FeCO whole 4. In case of H2 and H2S, they are not that much acidic, so their hydridic character is actually remaining intact. But in case of HCOCO whole 4 and H2FeCO whole 4, not their hydridic character but their protonic character actually comes into picture. Now here we are actually have come to the last question of this discussion, that is showing two different cases which state different characters of a transitional metal hydride complex. Now two basic examples I have actually brought here. One is the HCOCO whole 4, which is reacting with water, where it is actually acting as a proton donor. And the next one is the hydride donor ability, that is the C5H5, that is CP FeCO whole to H, that is reacting with this HCl, which is very strong bonded acid. So in the first example, this HCOCO whole 4 is behaving as a proton donor or as an acid. So this metal carbonyl hydride will be acting as an acid. So here you see, because H2O is a very weak base, and it is, but since this is a very strong acid, so this acid base reaction takes place. So this molecule will I have in the last slide I have showed that this is having a pK in the range 1, so it is highly acidic in nature. So it will protonate the very low Lewis basic, this H2O or water molecule, to form this hydroxonium anion, that is H3O plus, and it will go to its stable form, that is CO whole 4 minus. You see, because what is the reason behind this molecule so much acidic in nature? Because this carbonyl in here is in zero form, or in the low oxygen state 0, it is having a electron count 4s to 3d7, because it's a D9 system. So 9 electron plus 4 into 2, that's 8 electron from the carbonyl. So 9 plus 8 is 17, and the negative charge, that is 1, that's 18. Since this is an 18 electron complex, so from 18, so it actually it is actually prone to come to this stable 18 electron complex. That's why it is very much acidic in nature. So this H plus is actually used to protonate this H2O, which is not that much Lewis basic. The next example actually goes in the range of this hydride vulnerability. So a similar metal carbonyl hydride is there, but just like the opposite to this one is actually a source of hydride. The reasons are actually ample because you see here all the ligands were pi acidic, only hydride was there, which is for a sigma donor. But in this case, only two pi acidic CO molecules are there, but the C5H5 minus, but the CP minus or the cyclopentadienyl anion, which is a very strong sigma donor ligand but not a good pi acceptor at all. So these actually increases the electron density on the metal center. That's why the hydridic character of this H minus increases, and now it is treated with the strong bond strategies, that is the HCl, which is a source of H plus. So if we are actually producing this H minus and H plus, they will be bound to one another as H2, and then the corresponding C5H5 FeCO whole to Cl molecule will be formed. So in this case, you have actually come to the conclusion that depending upon the ancillary ligands, the metal carbonyl hydrides will behave. And here also molecular dihydrogen is eliminated, which is one of the major driving force behind this reaction. So with this, these are the actually content I have prepared for this session. Now you can actually go through all the slides, or you can ask questions if you have any of the doubts regarding any of the slides.